Yeah, it's practice exam 3B. So this question, Rick T. Cat, up to his shenanigans, their lab discovered a new element. They've dubbed it nitnium. Nice ring to it. So, nitnium oxide, we're told, forms a basic solution at 25 degrees Celsius, and we want to know what type of element nitnium is. So remember, there is a quick and easy trend you can use for oxides. Oxides are just compounds that consist of oxygen and one other element, and they're neutrally charged. Anyway, here it is. So we have our little periodic table of the elements. We're talking about oxides here. Alright, so if we have a metallic oxide, those are basic. Now, there are some transition metal oxides that are amphoteric. Generally speaking, the further up and to the right we go, the less metallic character we have, the less basic our oxides are. Now, if we go up to the top right-hand corner of the periodic table, where we have our nonmetals, so the nonmetals, those are going to form acidic oxides. And then, along the stair step, the metalloids, they're not quite acidic oxides, they're not quite basic oxides, they're somewhere in between. These are amphoteric oxides. So this says that we're looking at a basic oxide. That means that we must be looking at a metal oxide. So it's going to be choice A for the win here. Okay. This next question says, which of the following choices is the best way to classify the CH3NH3 plus ion? And there's a few different ways you can think about this. Way number one, we're looking at something with a positive charge. In general, if chemical species have positive charges, they're going to be better at accepting electrons. So they're going to be better Lewis acids. Additionally, this has a positive charge on it, and it's not one of the following. So it's not lithium plus, sodium plus, potassium plus, calcium 2 plus, etc. So it's not a group 1 metal cation, and it's not a group 2 metal cation, calcium and below, like calcium 2 plus, strontium 2 plus, barium 2 plus. So what commonality do these ions have? Well, they're all directly related to our strong bases, right? So strong bases, like, for example, lithium hydroxide, potassium hydroxide, etc., dissociate completely in aqueous solution. They leave behind negligible metal cations. So, like, for example, the ones that we have listed here. Since this has a positive charge and it's not one of those, this is going to be an acid. And that's a good tried and true rule of thumb for this course. So cations that are not group 1 metal cations or group 2 calcium and below are going to be able to act as good Lewis acids in aqueous solution. Now the other way we can think about this is from a structural standpoint. So here we have the structure of methylamine. This is the conjugate base of our chemical species in question. So it's a good base because it has that lone pair of electrons on it. So what we're actually looking at in this problem is this structure. So this is the conjugate acid of methylamine. So for our purposes, all neutral amines are going to be weak bases. Therefore, all of their conjugates are going to be weak acids. So that's another structural way that you can think about this problem. This question challenges us to find the conjugate acid and conjugate base of the ascorbate ion. Ascorbate is C6H7O6-. So let's just do the more long-winded version of this first, and then we'll do the really quick way that you can answer a question like this. So the long way is to write out the actual chemical reactions that this can undergo. So here we have our ascorbate ion, C6H7O6-. First, let's figure out what its conjugate base is. So to find the conjugate base, we're going to treat this like it's an acid. So this can dissociate, and if we're treating it as an acid, it's going to be getting rid of an H+. So here's our H+, and that'll leave behind C6H6O6-2-. Okay, so that would be the conjugate base. If we want to find the conjugate acid, then we have to treat this like it's a base. So, again, here's our ascorbate ion. And if we're treating this like a base, let's just react it with water. Have it pluck a proton off. It becomes C6H8O6. Okay. And it would leave behind hydroxide in the solution as well. So this is the conjugate acid. The other way you can think about it is to find the conjugate base of something, all you need to do is pluck off a proton from it. Likewise, if you want to find the conjugate acid of something, all you have to do is add on an H plus to it. So that's the really quick way that you can go about doing a problem like this as well. Okay, so next we have a question that says, which of the following species will have a negligible effect on the pH of an aqueous solution? So Cl minus is the what of a what, therefore making it what? It is the conjugate base, you can't see this but I'm doing air quotes right now, conjugate base of a strong acid, therefore making it negligible. So if we think about HCl, it's a strong acid. So strong acids, what makes them strong is when they go all out. So when this dissociates, we use a full-headed arrow. Dissociates completely into H plus and Cl minus. And these two things, once they're broken apart, they are never, ever, ever getting back together. Like, ever, okay? So if we consider Cl minus, and we tried to react it with water, so if we tried to hydrolyze water with Cl minus, is there any way that it could pluck a proton off of water to reform HCl and leave behind hydroxide? Well, if Cl minus can't grab on to a proton freely floating in solution, so if it can't grab onto a proton that's freely floating in solution to reform HCl, is there any way that it's going to be able to break a covalent bond in water to form hydroxide? No. It's actually a weaker base than water's auto-ionization is. So this reaction, not going to happen here. That's why it's going to have a negligible effect on the pH of a solution. So the conjugate of a strong acid is always going to be a negligible base. Okay, up next we have benzimidazole. There's the structure. It's an important organic base, and it's actually a portion of vitamin B12. Neat. So, we want to know what is going to be the pH of the solution at 25 degrees Celsius, and we're given a Kb. So anytime you want to find the pH of a weak acid or weak base solution, when in doubt, ice it out. And I'm just going to write the generic reaction here. We've got our base here. You could find the formula if you want to, but it's not necessary. All weak bases are going to do basically the same. They're going to go through the same motion. It's the same script, just different characters. So, for any weak base, we're going to react it with water, because the water is going to be the source of the hydroxide. And they're going to form the conjugate acid, BH+, and hydroxide. So now what we're going to do is we're going to write out our ICE, and we're going to plug in everything we know. So we know that we're starting with 1.5 molar of that. We don't have water. Well, water, we don't care. We love it. The conjugate acid, we have 0 of, unless told otherwise. And hydroxide, 0. Our change is going to be minus X, plus X, and plus X. And we're going to be left with 1.5 minus X for the equilibrium line for the base. 0 plus X is X, 0 plus X is X. And we know that that minus X is going to be negligible compared to the 1.5 molar, but not compared to the 0. But more on that in a moment. So we're halfway done with this problem. Now we need to write out our equilibrium expression. So Kb, we have our products over our reactants. Now let's plug in our numbers. It's 3.98 times 10 to the negative 9th. That's our Kb, is equal to x times x, which is x squared, over, and once again, this minus x is going to be negligible compared to the 1.5 molar already present. So we can just get rid of that. And this is just 1.5. So we'll multiply the 1.5 through. We'll get 5.97 times 10 to the negative 9th is equal to x squared. And then we'll take some square roots. And we'll get x is equal to 7.73 times 10 to the negative 5th. Now, always remember to check, what are we solving for here? What is x the concentration of? X is the concentration of hydroxide, right? So if we take the negative log, we're getting the pOH of the solution. So when we take the negative log of 7.73 times 10 to the negative 5th, that's the pOH. So do the negative log base 10 of this. And that gives us our pOH is equal to 4.11. Now, are we solving for pOH? No, we're solving for pH. So at 25 degrees Celsius, we know that pH plus pOH equals 14. So we'll subtract 4.11 from 14, and we'll get our answer, which is the pH is equal to 9.89. Our choice E. Alright, here we're going to do a little analysis of 5 chemical species and try to figure out which ones of these have a pH that is less than 7. So pH less than 7, we're looking for acidic species here. Okay, so the first one is ammonium chloride. So ammonium salts are, whenever we have a nitrogen that has 4 bonds on it, we have a positive, we have a cation. And that's just being counterbalanced in this case by the Cl-. All ammonium salts are acidic. So this is going to dissociate completely into NH4+ and Cl-. Now Cl- is the what of what, therefore making it what? That's right, it's the conjugate base of a strong acid, therefore making it negligible. But all ammoniums with their positive charge, so it has a positive charge, it's not a group 1 metal cation or a group 2 metal cation, calcium and below. So this is going to be acidic. Okay, and we're looking for acidic chemical species here. So this one is going to get a check. Calcium oxide, we already talked about the rules for oxides. Metal oxides are basic, so I should think not. The next one is sodium nitrite. Sodium nitrite is a salt that would dissociate into Na+ and NO2-. Now NO2- looks an awful lot like one of our favorite negligible anions. It looks like NO3-, but it's not. So, is it the same thing? No! Get it? NO2. Anyway, it has a negative charge, and it's not the conjugate of a strong acid, therefore it can act as a base in aqueous solution. So this is also a basic salt, but we're not looking for basic salts, we're looking for acidic salts. Up next we have potassium perchlorate. Potassium perchlorate would turn into K+, which is negligible, and perchlorate, which is also negligible. These are the conjugates of a strong base and a strong acid, respectively. So this is going to be a neutral salt. Finally, we have acetic acid, CH3COOH. This is a classic weak acid. We've used this example a lot. It dissociates partially into acetate, or as I like to call it, CHCOOH. Yeah. So this being a weak acid, it's going to form, well, also an acidic solution. So our answer is 1N5 only. Okay, this next question is about a very popular molecule, ibuprofen. So ibuprofen is a notable blocker of inflammation and pain. It's also a weak acid, and it's a weak acid by virtue of having a carboxylic acid functional group on it. So, for weak acids, when in doubt, ice it out. And our reaction? We could find the formula of this if we want to. It's not necessary, though. We can just use generic weak acid HA. You can react these with water, too, if you want to, but for weak acids, it's generally easiest just to make it dissociate into H+ and the conjugate base. And again, we could react this with water to form H3O+. It's not going to change our ICE table and equilibrium expression. But, so I just like to do it this way because it's a little bit simpler. So then, for any weak acid, when in doubt, ice it out. Plug in what we know. So this is actually going to end up being a reverse ICE table. And what I mean by that is we're given the initial concentration of ibuprofen. which is 0.55 molar. And in this case, though, we're not given a Ka value. In fact, our task here is to solve for our equilibrium constant. So that means we must be given some other piece of information, and indeed we are. We're given the pH. And remember, if you know the pH of a solution, you can always find the H plus concentration. So let's do just that. Our pH is equal to 2.58. And remember that pH means the negative log base 10 of the H plus concentration. Also, I apologize that the full solution keeps magically appearing. So, full disclosure, the original recording of this was deleted. The program kept, however, my annotations, so populating them in, but the populate one at a time button is right next to the let's just throw everything in button. So everything is getting thrown in. Yeah, good times. Anyway, if you know pH, you can always find the H plus concentration. So, remember, pH means the negative log base 10 of something. So, all I'm going to do is move the negative sign over. I'm going to multiply both sides by -1, and then take 10 to both powers. When we do, we'll end up getting that the H plus concentration is 0.00263. Okay, great. So, that's going to be our equilibrium concentration of H plus. We're starting with 0, and we're ending with 0.00263. Now then, if we know the equilibrium concentration of H plus, since it's a 1-to-1 ratio of H plus to A minus, that means that the equilibrium concentration of A minus is also going to be 0.00263. Okay? And if we know the initial amount, which is 0 for both of these, and we know the equilibrium amount, which is 0.00263, that means that the change for each of these is going to be plus 0.00263 and plus 0.00263. Now then, we could technically find the equilibrium, the precise equilibrium amount of HA. So I'm going to do that. It's not necessary, though, because we'll see if we subtract the 0.00263. We oftentimes make the assumption with weak acids, well, not oftentimes, we always make the assumption with weak acids, if the K values on an order of 10 to the negative fifth are less, that the change is going to be insignificant compared to the initial amount there. And this will actually kind of show us that is indeed true. So if we subtract the 0.00263 from 0.55, we end up getting 0.547, which within our realm of precision is basically the same thing as 0.55. Now, that being said, we don't know necessarily if this is going to end up being on order of 10 to the negative fifth or less, so can't hurt to do it, but not going to change our calculations. We could plug in the 0.55 or the 0.547 and still get the right answer. So now we're going to write our equilibrium expression out. Ka is equal to the concentration of acid times the concentration of the conjugate base, all divided by the concentration of the acid. Now plug in all the numbers that we know. So Ka is going to be equal to 0.00263 times 0.00263. Throw some brackets around these. All divided by the 0.547. And now we're going to have our Ka value, which is equal to 1.26 times 10 to the negative fifth. Cool. Okay, up next we have a titration enthusiast doing a titration for the sheer thrill of a titration. Yes, indeedy. And they're using lactic acid. So here we have lactic acid, and what we're going to do for a titration is we can make this a little bit simpler. So we're adding in, as we can see in the problem, a strong base. It doesn't matter what strong base we use. So I personally like to cross out the K plus and just make this OH minus because it's a source of the hydroxide anion. Okay, so now what we're going to do is, when in doubt, for titration, is it out. Titrations always use ICF tables. And so here is our lactic acid, C2H5OCOOH. We could also just write out HA if we wanted to. Going to react it with OH minus. And titrations always use a full-headed arrow because they're always involving strong acids and strong bases. So when they go all out. So the hydroxide is going to keep ripping off protons and keep ripping off protons to make the conjugate base until we run out of the limiting reagent. And when it does, it's going to form H2O liquid. So then we'll write out our ICF table. Plug in everything we know. Now remember, ICF tables differ from ICE tables for two key reasons. One are the units that we use. So ICE tables use molarity, or in the case of gases, atmospheres. ICF tables use moles, always use moles. And so to calculate moles, we use the relationship that moles are equal to molarity times liters. So let's find the moles of each of these for the for the lactic acid, excuse me. It's 2 molar, and it's 500 milliliters, which is 0.5 liters, which gives us 1 mole of that. Then we'll calculate for the hydroxide. It's 1 molar times 0.5 liters, also 500 milliliters, which is 0.5 mole of hydroxide. At this point, you might recognize that this is a half equivalence point titration, in which case all you have to do is one quick calculation. I'm going to go through the whole ICF table, though, just because it can't hurt. We've got 0 of that, and we don't care about the water. I mean, we do care about water, just not in ICE and ICF tables. So we're going to have minus 0.5 because our limiting reagent is the hydroxide. It's going to keep reacting until that hydroxide is used up. So it's going to be minus 0.5, minus 0.5, and over on product side it's going to be plus 0.5, which leaves us with 0.5 moles of the lactic acid, 0 of the hydroxide, it's all used up, and 0.5 mole of lactate, the conjugate base. Wait a minute! Hark! We have a weak acid, and its conjugate weak base, together in appreciable concentrations in a solution. We've got ourselves a... Oh my goodness, we have a... Buffer alert, buffer alert, buffer alert. Whenever we recognize that we have a buffer, buffers are great for, well, 2 main reasons. One, they're absolutely critical for controlling pH and accordingly help us to survive. Thanks, buffers. But also, mathematically, they make our jobs a lot easier because it's really easy to calculate the pH. Once you recognize a buffer, you can use the Henderson-Hasselbalch equation, which is pH is equal to pKa plus the log of the base to acid ratio. And it doesn't matter if you use moles or millimoles or millimolar or molar or millimoles per deciliter. Doesn't matter. As long as you're consistent with your units, it is a robust equation. So, now plugging in our values, P always means the negative log, so the pKa is going to be the negative log of the Ka that we're given, 1.4 times 10 to the negative 4th, plus the log of our base concentration, which is 0.5, over our acid. These aren't the concentrations. These are the number of moles. And any number divided by itself is just 1. The log of 1 is 0. So actually, that ends up canceling out. And we end up getting pH is equal to the pKa, which is 3.85, which rounds up to 3.9. So this question tasks us with finding the strongest, which one of these is the most basic. The highest pH means the most basic. So, whenever we're thinking about these anions here, so all of these are sodium salts. Sodium is negligible. Na plus is a group 1 metal cation, and we know that those do not contribute to the pH of a solution. So it's oftentimes easiest to think about the strength of the conjugate acids here. So what I'm going to do here is consider the conjugate acids of each of these bases. So the sodium doesn't matter. The sodium is negligible. And what we're going to do is come up with the conjugate acids of these 5 different anions. So the first one is chlorous acid, HClO2. Then we have perchloric acid, HClO4. Then we have bromous acid, HBrO2. Then we have perbromic acid, HBrO4. Then we have hydrochloric acid, HCl. Now, the first thing I would do is eliminate anything that is any strong acids, because the conjugate bases of strong acids are negligible. And if we look at these, 2 of these should stand out as being strong acids. HClO4, so that means ClO4 minus the perchlorate anion is going to be negligible, and HCl. Now, between these, which one of these is the weakest acid? Because we know the weaker the acid, the stronger the conjugate base. the weakest acid is going to give us the strongest conjugate base. Okay. So if we compare these, HClO2, HBrO2, and HBrO4, HBrO2 has the least electronegative central atom, the bromine, and only 2 oxygens as compared to the 4 from HBrO4. So, the least electronegative central atom and the fewest number of oxygens makes for a weaker oxyacid, which makes for a weaker acid, and therefore a stronger conjugate base. So BrO2- is the strongest of the bases here. Alright, up next we have a question about palmitic acid. So palmitic acid is important in biosynthesis because it's actually a common metabolite that's made during processes that turn excess carbohydrates into fat. So it's important in mammals. It's also, fun fact, in its triglyceride form, is one of the main components of butter. Anyway, so it is also a weak acid. We could write out the entire formula if we wanted to, but it's not necessary. So in our reaction, we could write C15H31 COOH. We can also just treat it, it's like a run-of-the-mill generic weak acid, HA. So anytime we want to find the pH of a weak acid or weak base solution, when in doubt, ice it out. I'm just going to write HA here because we don't need to actually write out the full formula. It's going to dissociate in an equilibrium reaction into H+, and the conjugate base, palmitate, which we're just going to call A-, ICE, then plug in what we know. So we know that we have a 0.5 molar solution. We're starting with 0 H+ and 0 A-. Our change is minus X plus X and plus X. So we end up with 0.05 minus X. 0 plus X is X, and 0 plus X is X. Okay, now we are halfway there. Whoa. Now we need to write out our equilibrium expression. Ka is equal to products over reactants. So there we have our generic version of our equilibrium expression. Now let's plug in our numbers. X times X is X squared. Our Ka is 1.66 times 10 to the negative fifth. And our initial concentration is 0.05. As always, we don't need to consider the change here because our Ka is on order of 10 to the negative fifth or less. Well, it's on order of 10 to the negative fifth. So we can assume that the change is negligible, so we plugged in the 0.05. We solve for X, and then, since X represents the concentration of H+, when we take the negative log, we end up getting the pH, which is 3.0. This question involves sodium cyanide. So sodium cyanide is wildly toxic. It ends up binding irreversibly to complexes in mitochondria, but it's also actually commonly used in a process called leaching to get certain precious metals like gold and silver. So the first thing I always like to do in an acid-base problem is ask myself, is the thing that we have a K for the same exact chemical species as what's in our problem? So is HCN the same exact thing as NaCN? And the answer is no, but they're awfully similar. So NaCN is a salt. So NaCN will dissociate completely into sodium plus, which is negligible, and the cyanide anion. Well, how is cyanide, Cn-, related to hydrocyanic acid, HCN? They're conjugates of each other, right? So, that means that we're actually dealing with the conjugate base of a weak acid, which is a weak base. And how much of it do we have? Well, since we're starting with 1.5 molar of the NaCN, all of it's going to dissociate, so we're going to end up with 1.5 molar of the Cn-. Now, we're going to treat it like we treat any weak base in this course. We're going to react it with water for our reaction. And then when we do, it's going to be an equilibrium process to make the conjugate acid HCN and leave behind hydroxide. Water is the source of our hydroxide here. So any weak base solution, we're going to need to react with water. We'll do our ICE table. We've got 1.5 molar Cn. We don't care. 0 of the HCN, 0 of the OH-, minus X, plus X, plus X. To give us 1.5 minus X, X, and X. Now we'll write out our equilibrium expression. Now note, this is base hydrolysis. This is a Kb reaction. So when we plug in a value for our equilibrium constant, we need to use a Kb. But we're given a Ka. Whatever can we do? We can use this relationship. The Ka times the Kb of a conjugate acid-base pair is equal to the auto-ionization constant of water, Kw, which at 25 degrees Celsius is 1 times 10 to the negative 14th. So, let's solve for that. Our Ka of hydrocyanic acid is 6.2 times 10 to the negative 10th. Kb is what we need here, and it's equal to 1.0 times 10 to the negative 14th. When we solve for Kb, we end up getting that Kb is equal to 1.61 times 10 to the negative 5th. Cool. Now we have everything we need to solve for x. So 1.61 times 10 to the negative 5th is equal to x times x, which is x squared, over 1.5. As always, we can simplify this and assume that the change is negligible compared to the 1.5 molar that's initially there. Solve for x, we get x is equal to 0.0049. Take the negative log of that. So negative log of 0.0049 is our POH, because remember, this represents the hydroxide ion concentration, the OH minus. So whatever we're getting here is the POH, but we actually want the pH. So all we have to do is subtract that from 14. The POH is 2.31, and we end up getting the pH is 11.69. This question is pretty straightforward. We're asked to find the pOH of a strong base solution, barium hydroxide. So a strong base, does it react a little bit? Is maybe 1 out of every 100, 1 out of every 1,000 going to dissociate? Nay, all of it. This is a strong base. When it goes all out. So we just need to keep in mind that for every barium hydroxide, there are actually 2 hydroxides. So it's going to dissociate into 2 OH minuses for every barium hydroxide we have. So really all we have to do is take that initial 0.025 molar and then use a little bit of stoichiometry. So for every 1 molar of barium hydroxide, it's actually 2 molar of hydroxide, which ends up equaling 0.05 molar OH minus. So now when we take the negative log of this, we end up getting the POH, which is what we're trying to find. And that happens to be 1.30. Cool. Up next, on the basis of the following data for degree of ionization for 0.1 molar solutions, select which acid has the smallest Ka. So the larger the Ka, the stronger the acid. The stronger the acid, the more it's going to dissociate. The greater percentage of it is going to ionize. And the percent ionization is based on both the Ka of an acid and also the initial concentration. But here we have an equal playing field. Everything has the same initial concentration, which means the one that ionizes the most is going to have the highest Ka. That's the HCl. It's a strong acid, more like 99.999%, but whatever. The one that has the least percentage is going to be the weakest acid and have the smallest Ka, which is acetic acid, CH3COOH. Okay, up next, we're told here, no, this one comes out and just tells us right off the bat we're looking at a buffer solution. It's 0.244 molar acetic acid, a lot of acetic acid questions in here, and 0.122 molar sodium acetate. What is its pH at 0 degrees Celsius, and then we're given the Ka of acetic acid. Okay, so whenever you have a buffer, we can use Henderson-Hasselbalch. So let's do just that. So we're told here it's a buffer. No need to identify it, but we can identify it as a buffer solution given that we have a conjugate weak acid, weak base pair here. The pH is equal to pKa plus the log of base over acid. Alright, so our pH is going to be equal to the negative log of our Ka, which is 1.64 times 10 to the negative 5th at this temperature, plus the log of our base, which is 0.122 molar, that's the sodium acetate, over the acid, which is 0.244 molar. And, oops, it didn't write in the log here. Let me write in the log. Well, first, the pKa ends up being 4.79. Cool. And now let's correct this. There we go. Forgot to write in the log. Sorry about that. So the log of, well, 0.122 divided by 0.244 is 0.5, and the log of 0.5 ends up being negative 0.3. So when we add these two together, we end up getting the pH is equal to 4.49. All right, up next, we have a question about a polyprotic acid, phosphoric acid, H3PO4. I highly encourage you, write out all of the dissociations here for Ka1, Ka2, and Ka3. That really helps us visualize the answer here. So I'm going to write out each reaction. Ka1 is when we have our fully protonated H3PO4. It dissociates into H+, classic acid behavior, and H2PO4-. Cool. Now for Ka2, we're going to take that H2PO4-, and we're going to dissociate it into H+, and HPO4-2-. But wait, there's one more. Now for Ka3, we're going to take that HPO4-2- and dissociate it into H+ and phosphate PO4-3-. Okay, so first let's identify what's amphoteric in this reaction. So H3PO4 can dissociate into H+ and H2PO4-. So it can act as an acid, but not so much a base. However, when it dissociates, we end up getting H2PO4-. Now notice, this is a weak acid dissociation. So H2PO4- can actually grab onto a proton and reform H3PO4. So that means it can act as a weak base. But hark! This is a polyprotic acid. It also has a proton it can give up. So it can also then go through this Ka reaction where it dissociates to form H+ and HPO4-2-. So it is amphoteric. Same thing with HPO4-2-. This reaction could go this direction, so it can reform H2PO4-, but it can also dissociate further into phosphate and H+. So H2PO4- and HPO4-2- are both amphoteric species. Now the second part of this question asks which of these is the strongest base. So the strongest base, we know that the relationship for a conjugate weak acid weak base pair, actually really for any acid base pair, is that Ka of a conjugate acid times Kb of the conjugate base is equal to a constant Kw. That means the weaker the acid, the stronger the conjugate base. All polyprotic acids get increasingly weaker with every dissociation. So Ka3 will always be less than Ka2, which will always be less than Ka1. So since Ka3 is the weakest acid, it's the weakest dissociation, that means that its conjugate base will be the strongest. So phosphate is going to be the strongest base here. Okay. So PO4-3- is going to be the strongest base. With this next question, we're kicking it a little old school here because we're actually looking at Le Chatelier's principle. And there's two different ways of thinking about how this reaction is going to work. So, we're adding in hydroxide, a strong base, sodium hydroxide. Doesn't matter which hydroxide we add in to this aqueous solution. So if we think about the relationship between hydroxide and hydronium, H3O+, they are antagonistic to each other. So H3O+ times OH- concentration is equal to a constant, Kw, which means as hydroxide goes up, H3O+ goes down. The other way we can think about this is if we're adding in hydroxide, what is the hydroxide going to preferentially react with in terms of all four of these chemical species? Well, it's going to preferentially react with the H3O+. So hydroxide, because it reacts with hydronium to form water, this is going to end up using up our H3O+. So either way you think about this, our H3O+ concentration is going down, which means that this reaction is going to shift to the right. And then we can answer everything here. So statement 1, Ka will increase. Will the acid dissociation constant, you can't tell but I'm winking right now, will the constant change for this reaction? Well, no. The only way to change the constant is to change the temperature. What we will change is Q, so it'll have to re-equilibrate by shifting to the right, but the Ka will not increase. Delta G will decrease. This reaction becomes more spontaneous as written. Delta G will indeed decrease. The pH will increase. Anytime you add a strong base into an aqueous solution, the pH is always going to increase. We're making it more basic. So indeed, that's going to happen. The concentration of aspirin will decrease. So since this reaction is shifting to the right, that means that our reactants are going to go down, which means that our acetylsalicylic acid is going to decrease in concentration as well. Yep. And then finally, the reaction will shift to the left. Lol. In fact, I'm going to write out lol. It's not going to shift to the left, it's going to shift to the right. Myth busted. So 2, 3, and 4 only are correct. This question says, what is the hydroxide ion concentration in 0.03 molar solution of nitric acid, HNO3? So HNO3, it is a strong acid. It doesn't matter if we're looking at HCl, HBr, HI, HNO3, HClO3, or HClO4. H2SO4 is a little wacky because it's a strong acid, but then it has a fairly strong acid as its conjugate base with a Ka of 1.1 times 10 to the negative 2. So we're not going to be evaluating that because it gets too mathematically wonky. Anyway, does it matter which strong acid we use of those other 6? No. It's just a source of H+. So I like to cross out that and just write in H+ instead. So we have 0.03 molar solution of H+, and we want to find the hydroxide, the OH- concentration. Now, any aqueous solution will have both H+ and OH-. This is an acidic solution, so it'll have far more H+ than it'll have OH-, but we can still calculate the OH- concentration. Using this relationship, the concentration of H+ times the concentration of hydroxide is equal to our constant Kw. So, at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the negative 14th. We know that our H+ concentration is 0.03, divide both sides by that, and we'll get that our hydroxide concentration is 3.33 times 10 to the negative 13th. Yikes, that's small. We have a far greater concentration of acid, and that's what we would expect, of hydronium, and we would indeed expect that from an acidic solution. This question says, which of the following statements is true about acid-base chemistry? In an acidic solution, the hydroxide concentration is greater than the H+. No, we just talked about this. No, that's just goofy. That would be a basic solution. For generic weak acid, HX, the H+ concentration is less than the HX. Well, let's think about this one. If we consider a generic acid, HX, and it dissociating into H+ and X-, the conjugate base, by definition, weak acids have a K that's less than 1. So that means that reactants are always going to be favored for a weak acid dissociation in water. So since the reactants are favored, that means that at equilibrium, HX will be greater than the H+ concentration. So this one is indeed true. Now to go over the other ones, ClO3- is a weak base in aqueous solution. ClO3- is the what of a what, therefore making it what? It's the conjugate base of a strong acid, therefore making it negligible. So that is false. The next one says if pOH is greater than pH, then a solution is basic. So this one, I'd like to take a step back and think about actual tangible numbers here. So let's say that we have a solution that's acidic. So let's just say, hypothetically, we have a pH of 3. Well, 14 minus that at 25 degrees Celsius is going to be a pOH of 11. We can see that for an acidic solution, the pH is less than the pOH. So what about a basic solution? So let's just say a pH equal to 10. Well, then the pOH would be equal to 14 minus that, which would be 4. So in a basic solution, we can see here, as per this example, that the pH is greater than the pOH. So because P means the negative log of something, that means the smaller the value of pH, the more hydronium you have. The smaller the value of pOH, the more hydroxide you have. So if pOH is greater than pH, that means that you have more H+, and you would indeed have an acidic solution, not a basic solution. Finally, it says the Ka of H2O is greater than the Ka of H2SE. Let's draw out some structures to help us think about this one. So H2O looks like this. It's amphoteric, not super acidic, not super basic. Water does its kind of own thing. Now, selenium is in the same group as oxygen. It's just further down. So selenium is much larger than oxygen. That means that it forms longer bonds. Now remember, longer bonds are weaker. They're easier to break. So it's much, much, much easier to break this hydrogen-selenium bond, which means this is a stronger acid, which means it would have a greater Ka. So this is also false. This question says, please rank the following anions in order from least to most basic. Again, whenever I see a question about ranking anions, I like to think about the conjugate acids, because ranking acids, especially oxyacids, is a pretty straightforward process. So let's draw out all the conjugates here. I'm just going to replace the minuses with hydrogens to think about the conjugate acids. Okay. Now, for any oxyacid, remember the inductive effect tells us that the more electronegative atoms that you have that are in proximity to that OH bond, the more you polarize that OH bond, the stronger the acid becomes. And again, an oxyacid is an acid where you have an OH bond that you're hydrolyzing. Additionally, all of these are carboxylic acids. They all have that COOH motif. So we can make a stronger carboxylic acid by adding in more electronegative atoms. So which of these has the fewest number of electronegative atoms? Which of these would be the weakest acid? So I'm going to rank the conjugate acids. The weakest one would be 4. It only has 2 chlorines and 1 hydrogen. Now, what would contribute more electronegativity than 2 chlorines? Well, how about 3 chlorines? But wait a minute. What would contribute more electronegativity than that? How about 2 fluorines and 1 chlorine? But wait, how can we make it even stronger? What if we just have 3 fluorines? In fact, trifluoroacetic acid it's like acetic acid, except instead of having the 3 hydrogens coming off of that terminal carbon, it has 3 fluorines. It's actually 10,000 times stronger than acetic acid, so it does have a notable effect. And then remember our relationship, that for a conjugate acid-base pair, the weaker the acid, the stronger the conjugate base. So our bases here are going to be ranked in reverse order. So our weakest is going to be the conjugate base of the strongest acid, which would be choice 1, then choice 3, then choice 2, then choice 4. Okay, here we have the trickiest type of titration. We have a titration into a buffer solution. And really, titrations into buffer solutions aren't bad if we just remember that acids always react with bases and bases always react with acids. So remember, a titration is when you add a strong acid into a base solution or a strong base into an acid solution. So, we have one of 2 generic reactions. If we have a weak acid, well, a buffer solution by definition has a conjugate weak acid, weak base pair. So if we have a weak acid, and we have a weak base, and we add in hydroxide, what will the hydroxide preferentially react with? The weak acid component or the weak base? Well, it will react with the weak acid component. So here we have just some generic weak acid and conjugate weak base. If we add in hydroxide, which is what we're doing like in this problem, again, whenever I see a strong base or a strong acid, I like to cross out the negligible species. Na plus is negligible, not going to contribute to the pH of the solution. So our reaction is going to be HA plus OH minus. And when these react, they go all out. These are a full-headed arrow. And this will form H2O and the conjugate base. If we added in an acid, the acid would preferentially react with the basic component of our buffer. And we get A minus plus H plus yields, the conjugate acid. Since we're titrating in the strong base, that means it's going to be reacting with the weak acid component. So, our reaction is going to be HClO2, that's our weak acid, plus hydroxide, doesn't matter what hydroxide we use, yields H2O H2O liquid and ClO2 minus. There we go. Okay, so for any titration, when in doubt, ISF it out. We'll use an ICF table. Plug in the number of moles. So let's do each of these calculations. we have a 1 liter solution of 1 molar HClO2 and 1.2 molar ClO2 minus. I cross out the sodium because the sodium doesn't contribute to the pH here. So it's 1 molar HClO2 times the 1 liter of solution, which is 1 mole. So we've got 1 mole of that. Now remember, we also have our 1 liter also contains 1.2 molar ClO2 minus. So 1.2 molar ClO2 minus times 1 liter is 1.2 moles. Plug that into our table. And then finally for hydroxide, it's 2 molar, and it's only 200 milliliters, which is 0.2 liters, which is 0.4 mole. Okay, so we're going to plug that in. Find our limiting reagent. It is the hydroxide, so it's going to be minus 0.4 mole of that, minus 0.4 mole of that, and plus 0.4 mole for the products, which gives us 0 of the limiting reagent, 0.6 moles of the HClO2 remaining, and 1.6 mole of the ClO2 minus remaining. Wait a minute! Hold the phone! Conjugate. Whoop, didn't mean to cross that out. Hold the proverbial phone here. We have a conjugate weak acid, weak base pair together in appreciable concentrations. Oh my goodness, we're looking at a buffer. Woo! Which means we can use Henderson-Hasselbalch. Henderson-Hasselbalch again is pH is equal to pKa plus the log of base over acid. Now we'll plug in our values. So our pH is going to be equal to the negative log of our Ka, which is 1.1 times 10 to the negative 2, plus the log of, and our base concentration, the base number of moles is 1.6 moles. The acid is 0.6 moles. So we end up getting the pH is equal to our pKa, which is 1.96, and 1.6 divided by 0.6, if we take the log of that, we get 0.43. So this ends up being, the pH is 2.4. Well, 2.39, which rounds to 2.4. And my apologies when making this question. I think I made a typo in the answers, so I'm sorry that this does not match any of the answer choices. The closest one here is D, but my apologies for my error in making this particular problem. But this is the work that you would do, and we would end up getting 2.4 as our pH. So let's say 2.6-ish, because it's more like actually 2.4. In this problem, we're looking at a table of pKa values, and we need to find the strongest acid and the strongest base. So remember, pKa means the negative log of the Ka. So greater Ka means a stronger acid, but the greater the value of Ka, the more negative the value of the pKa, because Ka is the negative log of the Ka. So as pKa goes down, that means that our Ka goes up and we have a stronger acid. The strongest acid here is phosphoric acid. We can see it's right here. The only stronger acids that are given are the trifluoroacetic acid, the hydronium, the H2SO4, the hydrobromic acid, and hydroiodic acid, none of which are actually answer choices here. So the strongest of these acids is phosphoric acid. What about the strongest base? Now we can actually eliminate a number of choices here. So first of all, the first answer choice is an acid. And recall, we know that for a conjugate weak acid, weak base pair, well actually for any conjugate acid base pair, the weaker the acid, the stronger the conjugate base. The first one we're going to eliminate just because it is not in fact a base at all. We can see it's actually a pretty strong acid. So I'm just going to eliminate that choice. Choice B, could be possibly, that's a conjugate base. Maybe there's some better answers. We'll find out. The next one is ammonium. It is also an acid. We can eliminate that choice. The next one is the methyl anion. Methyl anion is a base. It's got negative charge. You can donate those electrons. And it's the conjugate base of methane, which is the last choice. Methane is such a bad acid. Look, it has a pKa value of 60. It's such a weak acid. Methane doesn't have any lone pairs of electrons, though, so it can't act as a base. Now then, it's such a weak acid that its conjugate base is really, really, really ridiculously strong. It is an immensely powerful base. A carbon with only 3 bonds is a very uncomfortable carbon. So if we compare these two possible choices, remember, the weaker the acid, the stronger the conjugate base. The weakest acid here is the methane, which makes this the strongest possible conjugate base. So, which of these following combinations can make a buffer? Now, there's 2 ways that we can make a buffer. The first is an inherent buffer is a conjugate weak acid, weak base pair. Okay, classic. The other way that we can make a buffer is through a titration. We can have a titration of a weak acid plus a strong base, or we can have a weak base plus a strong acid. But the caveat in both of these cases is we need more moles of the weak stuff. Reason being, let's do an ICF table to show how this can happen. So let's say we have a hypothetical weak acid, HA, and we add in a strong base, a source of hydroxide. They will react completely to form H2O liquid and the conjugate base. Now, if we consider an ICF table, if we have fewer moles of hydroxide in this case, so let's just say we have 1 mole of HA and 0.5 mole of OH minus. Water, we don't care, we love it, and A minus, we're not starting off with any of this. So if the limiting reagent is the strong stuff, it would be minus 0.5, minus 0.5, and plus 0.5. What did we just do? Well, after the reaction, we'll have 0.5 moles of the HA, we'll have 0.5 moles of the A minus. Oh my goodness, look at that! We have a conjugate weak acid, weak base pair together, appreciable concentrations, we have a buffer! Woo! So we can make a buffer through a titration. A weak acid plus a strong base, or a weak base plus a strong acid, but we need to have more moles of the weak stuff. Otherwise, we break our buffer. So let's look through these answer choices. HNO3, strong acid, plus NaNO3, which is a neutral NO3 minus a negligible base. No, this is just a really acidic solution. KCl plus HCl. Well, no, that's also just a neutral salt and a strong acid. NaNO2 and NaBr. NO2 minus is a weak base, and NaBr is a neutral salt, so this is just a weak base. HF and KF, we have a conjugate weak acid, weak base pair. The KF is just a source of F minus, so it's just F minus in disguise. Hey, look! Conjugate weak acid, weak base. That's a definition of a buffer. And then finally, we have sodium hydroxide, which is a strong base, and NaCl, which is neutral. This is just a basic solution. Up next, we're analyzing, trying to find where the buffer region is for this titration curve. Whenever we titrate, so this is a titration of a weak acid plus a strong base, we'll always go through this region where there is a slight change in the pH, but it's being relatively controlled despite the fact that we're adding in hydroxide. This is our buffer zone. After the buffer zone, when you've added in too much of the strong stuff, you hit a point in all titrations where either the pH will skyrocket or plummet. Remember, the midpoint there is called the equivalence point. And at the equivalence point, we've broken our buffer. There is no more buffer. If we keep going past this point, we're just adding in hydroxides, and we get a really, 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 really basic solution. So it looks like the pH is controlled there, but it's not, because there's nothing to mitigate the OH minus concentration. You're just making a solution that's more basic than a pumpkin spice latte. So the only buffer zone here is region A. So the top right is hydroxide city, population, well, hydroxides. And then finally, we have this question about a titration of a polyprotic acid. Whenever you have a polyprotic acid and you add in a strong base, what you end up getting is this really interesting curve that's basically multiple titration curves copied and pasted together. So there are 2 equivalence points in this, which means that there are 2 protons that can be taken off, which makes this a diprotic acid. And I'm going to quickly show you the whole layout, everything you would want to know about this sort of plot. So we have this initial buffer zone where we're adding in hydroxide and the pH is not changing that appreciably. There is a first half equivalence point. Cool. eventually we'd hit a point where the pH spikes. If we look at the halfway point, that's our first equivalence point. Neat. Okay. Then we hit another buffer zone. Whoa, cool. This is our second half equivalence point. Then we hit another spike. There's our second equivalence point. And then at this point, we're just adding in a ton of hydroxides, and the pH just ends up being really basic. So this is a diprotic acid. There are two equivalence points, which means there's 2 protons we can take off. So it must not be a triprotic acid, because it can't be both a diprotic and a triprotic acid. Then, if we look at what are the possible equivalence points, so point A is the first, point B is the first equivalence point, point D is the second equivalence point. So point E represents the third equivalence point. No, point E is just an arbitrary point where there's a lot of base added in. Point A represents the first half equivalence point. That is indeed true. The other thing that you want to know about these plots is that polyprotic acids have multiple Ka values. Therefore, it stands to reason it has multiple pKa values. So, at the first half equivalence point, pH is equal to pKa1. So that first proton dissociation. At the second half equivalence point, the pH is equal to pKa2. And that basically sums up what we want to know about interpreting these diprotic acid or polyprotic acid titration curves. So thank you very much for your time. Thank you for watching, and dominate the actual exam.